Good morning. My name is Wei Hu. I'm the Senior Vice President at Oracle working on mission-critical databases. I'm here today to share with you, talk about crypto-secure data management for healthcare using database blockchains. To start with, the problem that we're dealing with is really how do you protect your data from being illicitly modified or deleted? Okay. It's a sad reality out there that hackers are going after our data even now as we speak. And so the question is, what happens if a hacker finds a way to bypass the security mechanisms that protect your data, right? And these could be external hackers, these could be even rogue insiders, or more likely, compromised users. Suppose a hacker stole your passwords through social engineering attacks, phishing, and so forth, and log into systems as you, and then update your data without your approval. Okay. These are the kinds of threats that we worry about. Now, existing data is protected by mechanisms already, right? This is what security technology is all about. But they typically focus on keeping criminals out. For example, things like passwords, privileges, encryption, firewalls, and so forth. They're great and they're important. However, what happens if a hacker breaks through these things, steals a password, breaks through encryption, and gets access to your data? And that's where blockchain comes in. Right? Blockchain addresses these unavoidable vulnerabilities. It adds an extra layer of data security by protecting your data from being illicitly modified or deleted. Okay. And it uses technologies that come with blockchain, cryptographic digest, signatures, and distributed systems to implement what we call crypto-secure data management. Now, since you're attendees to this conference, you know that conventional blockchain is hard. Okay, it is very hard technology, but it is hard to implement. And here's some quotes of the web, right? How nobody understands blockchains. Blockchain is difficult, it is not easy, and overwhelming and frustrated to understand. Right? And blockchain is complicated because it requires new applications, new development methodologies, new data management products, and new business processes. And this is where we come in, which is, what if we can implement blockchain with your operational database? Right? Today, data are stored in operational databases like Oracle, MySQL, and so forth. Right? Now, information like patients, prescriptions, lab results, histories, they're all stored in databases, and these databases are typically called relational databases, which stores data like as tables. A table where each row is containing information about a specific person and so forth. So, for example, you may have a table containing patients, containing many rows, and one row of information for each patient, for example. Or a table called prescriptions, where each row can contain data about a specific prescription. Okay. And these databases, called relational databases, are accessed through standard programming interfaces, like SQL, standard query language, to access and query the data. And this is how these operational databases work. Now, conventional blockchains store the blockchain data separately outside of the relational database. And blockchains, use different programming interfaces, different APIs, right? And I think this is one of the reasons why conventional blockchains are hard. Developers know how to write software to use relational databases. All developers know SQL, right? But very few know how to develop this blockchain, right? And so the breakthrough that we're thinking about is, what if the blockchain is part of your operational database and supports the same APIs and SQL that developers used to? And that's what we did. Oracle makes it easy to implement blockchain. Okay. The Oracle database deeply integrates blockchain into the database. Okay. That makes it easy to implement blockchain with minimal application changes. Now, I talk about Oracle here, but Oracle, it represents a class of database called relational databases that are sort of the most prevalently used everywhere. Right? So the Oracle blockchain focuses on preventing illicit changes to data that records important information, actions, assets, entities, and documents. Examples, medical records, right? You don't want to change medical record, test results, prescriptions. Okay. And likewise, outside the medical realm, things like contracts, property titles, professional certificates, right? Diplomas, These kind of data that must be preserved and never modified. And this is the kind of data that can be deleted only when it is obsolete. Okay. And illicit changes to important records can result in loss of assets, legal exposure, loss of reputation, and bad medical outcomes. Right? And obviously, the worst case, the bad medical outcome would be death. And notice how the data that talk about here, medical records, test results, they're not really ledgers, right? And so this is why when it's part of an Oracle database, part of a database, you're not restricted to just protecting ledgers. You can protect other kinds of data also. And we can protect what's called reference data. Reference data, again, is data you can refer to, but you don't want to change. And I'll do that as a demo, okay, just to show you how it actually works. Okay. So I use a light example of movies. Okay, so here we create a table, customer sales of movies, and then we just say it's a blockchain table. Okay, so that's how we do it. This is standard SQL syntax. Okay, you type in and say, I want to create a table, make it a blockchain table. Now then, I connect to the database, and there's an insert, add some values, add some information about Top Gun 2, information about Avatar, and so forth. So adding data to this table. Okay. So this is a blockchain table, so I can clearly add data. Now, let's try to delete it, try to modify something, right? Now here, I'm logging as sysdba. Sysdba is a privileged user. It's basically administrator. It has all the privileges. And then it says, let me update the sales information and change this order. Right? There's other. And it says, returns the error. Can't do it. Okay? So this shows you that a blockchain table is a table we can add data, but you cannot modify existing data, okay? Even when you're a privileged user. Now, how does this work? Okay, so a blockchain table is really an immutable table that automatically changes new rows to existing rows cryptographically. Okay. And as I've shown you before, it's very simple. You simply add the blockchain keyword when you create the table. Say this is going to be a blockchain table instead of a normal table, if you will. Okay. And once you do this, data in this table can be added, but existing data cannot be changed or deleted by anyone using the database. And any newly inserted rows has a cryptographic digest that's computed based on the new row's contents. Basically, the entire row's contents compute a cryptographic digest, and then include a cryptographic digest of the previous row. And that's a new cryptographic digest. So this is how we chain the rows together. Each row's cryptographic digest depends on what's in this row, as well as the digest of the previous row. And so this just creates this chain of cryptographic digests. And then if anyone would modify any of the existing rows, the cryptographic digest would no longer match, because it would know the cryptographic digest would change, right? And then the next row wouldn't match and so forth. All right. So limiting damage from unavoidable vulnerabilities. We can never rid the world of hackers, or our tendency to click on unsafe links and so forth, right? So we cannot eliminate all security vulnerabilities, right? But we can limit the damage that they cause. Notice how the blockchain will not prevent your data from being stolen, right? You can still look at the data, right? If the hackers got in, they can look at the data. However, it provides an additional layer of defense that can prevent the dire consequences of your data being changed, right? But the way to think about it is, what's worse? Someone seeing my medical history, which is not good, right? Or someone modifying my prescription treatment plan. That is really bad. Okay? And likewise, from the financial realm, I don't want someone just look at my bank account balance. But far worse is someone stealing money in my bank account by modifying the account balances. Okay? And that's what we do. We limit the damage. Now, earlier on, I showed you an example of what happens when someone tries to modify the data. And the database catches that and prevents it. Right? Now, you might want to wonder, gee, suppose I'm a very good hacker, and what if the database software that enforces the immutability is bypassed? Suppose a hacker hacked the database software, right? Or got underneath the database. So this is what happens. Okay. So we did this experiment, which is that. So first you can see this. What if the hacker changes the data beneath the database, right? Suppose it got physical access to the machine, got physical access to disk drives, the flash drives, and somehow modify things, right? So here, we look at the price of a customer sale, right? And say the actual price is, say, $5, right? Now, in yellow, I go underneath the database, I get access to disk drives, through some extraordinary means and change the bit patterns on disk. Okay, and I'll describe it here. Now, I've changed the price. Now it's instead of $5, now it's say 10 cents, 0.1. Okay. So I've done that. Okay, I'm a great hacker. So what happens now is that we periodically run this verification routine to check the integrity of the blockchain. We call it just store procedure to verify the rows in this table. And it's going to signal an error. Say, gee, here is it, row verification failed. Something's wrong. In fact, based on the information, you actually select the row, look at what's in the row, and see indeed the data is wrong. Okay, so you can see that even tampering from outside the database can be detected because the cryptographic digests will no longer match. And we provide procedures to do this verification. You can just run this all the time. Now you can go a step further and say, what if I don't trust the Oracle to do the verification? What if the hacker was so good that even hacked the verification procedure? Well, this is where we come in. This is what we provide. The cryptographic chains in the Oracle database can be independently validated without using the database itself. Okay. We actually publish an open source library that can be run outside the database to read the chain data and verify the cryptographic digest, all independently of the database. So this provides independent validation. So even if someone were to compromise the database utterly, defeat the checks, defeat the verification routines, you can still validate the contents and detect that something bad has happened. I think that's really good, independent verification. And of course, because the blockchain is part of the database, it's fast. The response time of an insert can be sub-millisecond, which is unheard of for conventional blockchain. Now, we're going to talk about this a little bit later, which is that blockchain tables is part of what's called an Oracle database converged feature. It's not tied to a blockchain only database, because this database is not just for blockchain. It has other data and so forth, right? And notice how I've demonstrated that you don't require application changes. You just access using standard declarative SQL SQL, right? And of course, since these are relational tables, you can support full analytics and transactions on the table data. All right. So thinking further, you hacker, how do I detect a cover-up of illicit changes by authorities or very sophisticated hackers? Okay, so this takes a bit of explaining. Now, the cryptographic chaining of rows can be compromised if you have to perform very large-scale cover-up. Right? What if the hackers can access your entire database and rewrite your entire data from the very beginning, one row, second row, third row, every single row, such that they can recompute every single checksum to cryptographic digest, such that they all appear consistent, but they've rewritten all the data. Okay. Then the verification routines will not detect that case. Okay. Some examples of this kind of large-scale cover-up are orders given by corrupt executive or government authority to replace the database, right? Or sophisticated cybercrime organization that deletes and rewrites the entire database. This is where the feature we come in called the capability of distributing blockchain digest comes in. Okay. To detect this kind of cover-up, Oracle enables the cryptographic digest of the table to be distributed publicly. Okay. So these cryptographic digests, you can just send it out, right? They can be distributed periodically, like every 5 minutes, or when important data is inserted. Right? Now, it's actually safe to distribute these cryptographic digests because these digests computed from the data in the row, right? But from the digest itself, you cannot work out what the row contents were originally. So it's safe. Okay. And so what you can do is take the cryptographic digest and publish them to independent public store blockchain. You can email them out. You can post them on Facebook, Twitter, or I guess it's called X now. You can, publish it on, anywhere outside. But the whole idea is that you publish some third-party source that you don't control, right? And so what happens is then the verification routine can then just check these third-party sources and see what the published cryptographic digests are and confirm that they still match what's currently being, what the current digests are in the database. And that's how you detect a cover-up. Because the idea is that a hacker can hack the database, but they cannot hack all these third-party independent sources all at the same time either. Right? So this gives you the level of security that no one has hacked and overridden your entire data. Okay, so I've mentioned several times how blockchain tables are easier than peer-to-peer conventional blockchains, right? So let's review how does blockchain tables compare to conventional peer-to-peer blockchains. Now, a blockchain table with a publicly distributed signed digest is very similar to and provides most of the benefits of full peer-to-peer blockchain products. Because the public distributed signed digest is a way for third-party verification. Right? And so that you alone cannot do bad things, that third parties can verify and detect what's wrong. Blockchain tables prevent illicit changes made using the database, I've shown that, and detects illicit changes that bypass the database. Peer-to-peer blockchains can actually do more. They can provide strong protection by directly preventing all forms of illicit changes. That's because even if you bypass the database on one blockchain peer node, it's hard to imagine how you can bypass the security mechanism, all the peer rows. However, even though blockchain table does not detect, does not prevent if there changes, the fact that it detects them can also indirectly prevent most fraud. And the reason is criminals won't commit fraud if they know they will be caught. Right? For example, I would be really, really stupid to take a bribe while being videotaped, while being video recorded. Right? So that's why detection is actually a very strong deterrence in terms of prevention. So peer-to-peer blockchain is complicated. As we talked about before, you can prevent illicit changes that bypass database using a peer-to-peer architecture. Right? And it uses basically what's called consensus-based multi-party agreement for every change. So before I make a change, I make sure that my peers agree to the change. Right? And that prevents from a hacker from taking over a single database and compromise the entire system, because now you can compromise all the databases, right? Or at least the majority of databases. Right? However, that's great architecturally, but peer-to-peer is still vulnerable to common security vulnerabilities across all the peers. So you have a security vulnerability, say in Hyperledger Fabric, for example. Every single Hyperledger Fabric peer-to-peer will have the same security vulnerability, and so they can be all exploited. But that aside, the biggest problem with conventional peer-to-peer consensus, it requires new application development methodologies. And harder than that is changes the business processes and how businesses interact with customers, partners, right? So for example, imagine if you're a hospital and that you need to use a peer-to-peer system to make changes in patient records. What that means, before you can change your patient's record, you need to get agreement consensus with other hospitals. That's a very hard thing to do. Okay. So in summary, conventional peer-to-peer blockchain systems provide very effective illicit change prevention, but at the expense of significant complexity and trade-offs of mainstream use cases. That's one alternative. The other alternative to what we call integrating blockchains into your operational databases is to use specialized blockchain ledger-only databases. Okay. We chose to implement blockchain technology in our mainstream relational database. Okay. Other vendors may choose to do it differently. So for example, Amazon has this thing called the quantum ledger database that is a ledger database. And quoting them, it says, the transparent, immutable, and cryptographically verifiable transaction log. Okay. So a quantum ledger database is conceptually similar to Oracle blockchain table, except that it is a separate special purpose database just for ledgers. Okay. That means you have to deploy it as an additional database apart from your operational database. Okay. That is an architectural difference. So this approach that Amazon epitomizes is called using specialized databases. Right? And so, and I think this sounds very plausible when you start, right? Each specialized database excels in one aspect of application requirements. So if I'm using documents, I use MongoDB. If I use graph, I use Neo4j. If I want to do text searches, I employ Elasticsearch. If you want to use spatial, and so forth and so forth, right? But what happens is, as your workloads get more complicated, as your use case gets more, you keep on adding more and more databases. Right? And eventually you just end up with a lot of database types to manage. And that gets to be hard again, right? Now developers have learned to use all these databases, segregate the data, move data among different databases, right? And handle the differences, right? So this is the kind of thing that's easy to get started, but rapidly gets harder and harder. The approach two, which is the approach taken by database like Oracle, is to build what's called a converged database. And the Oracle database is both converged and complete. And we believe it makes it dramatically easier to develop and run modern applications. Okay? So the idea is that this single database type supports all the data types, all the workload types, all the analytics, right? And applications and users just call standard SQL for any of these data types. Okay? So you no longer have to fragment your data across different databases to support your application requirements. So as you, for instance, start with relational data and want to add JSON data, well, you don't have to change your database. You can just start using JSON type queries on the same data. Right? And of course, because it's all part of the same database, we take advantage of all the same scalability, availability, capabilities without sacrificing data consistency. And what's interesting is that with a converged database, you don't even have to compromise on functionality and performance. Oracle data technologies are really industry leading in each of these areas. Now, what I talk about is actually very, very hard. Right? Creating this fully complete database has taken the Oracle development teams, decades of efforts by thousands of engineers. Okay? But what we have is great. Now, I like to give the analogy, which is that the Oracle Converged database is a smartphone of data. You think about it, a few years ago, phones, maps like GPSs, music players, calendars were all separate products. Okay? You can go on and buy a PDA, you can go and buy an MP3 player, you can go and buy GPS systems and so forth. Now, all these products have gone away. They've all converged into features of a smartphone. We all carry a smartphone. Right? And similarly, new data technologies always come in the market. But then you can either build a specialized device or database for that new technology, or you incorporate it as part of an existing converged database like Oracle, right? The smartphone. Right? And converged features are easier to run and develop than separate products. Right? And the convergence allows new cross-feature innovations. So for example, on my smartphone, I can look at the address book and click on dial the phone number, right? And I can just look at the map and link back and so forth. So just much more powerful, much easier. And the analogy is, again, given that we all have smartphones, would you buy GPS today? Right? And so this is the argument I would give for why you want to use a converged database as opposed to a specialized blockchain-only database or a separate blockchain-only system. All right, so I'm going to wrap up. So the Oracle blockchain, there's so much possible ways to use blockchain, and I think it has been limited by just how hard it is. But because in-database blockchain is so much simpler, it is now usable in every industry and in majority of applications. Financial data, obviously assets, payments, insurance, logistics data, education data, degrees, certificates, certifications, professional history. You don't want those things to be forged, right? Government data, legal data, tax data, permits, titles, and so forth. Medical data, patients, test results, prescriptions, treatments, billings. All right, so I want to summarize. Number one, blockchain integrated into the database allows you to protect important data against illicit modification by hackers, rogue insiders, and massive cover-ups. And it's easily deployed with minimal application changes, right? Because there's now features of a converged database that can be used with all the other database features. There's access to standard programming language interfaces like SQL that developers are already familiar with. And so this allows you to effortlessly add blockchain integrity to database applications. Thank you.